Hey, what's up, YouTube? We're calculating the gravitational field strength at the moon's surface. Let's see how we're going to do that. We're going to start out with Newton's second law of motion, F equals ma, and it's the acceleration due to gravity. Newton also said that gravity is equal to his universal gravitational constant times the product of two masses divided by, you guessed it, their separation distance squared. So we set these two equal to each other, cancel out the tiny mass, and we can see that the acceleration due to gravity, let's just call it g, local g, is equal to that universal gravitational constant times the mass divided by, now the radius of the object squared. So we kind of think about like how far away is this mass from this, if this is you sitting on planet Earth? Well, even though you're sitting on planet Earth, you're not separated from Earth by a distance of 0. You have to approximate that all the mass of planet Earth exists at its center. And so you're separated from Earth by the radius of the Earth. So, well, here we're calculating it for the moon, actually. So it'd be the radius at the moon. So instead of you on the surface of the Earth, imagine an Apollo astronaut standing on the surface of the moon. All right, so this is the equation we need to calculate this, the gravitational field strength G. Let's plug in some values. So we've got G, which is 6.67 by 10 to the negative 11. And the units for that are going to be Newton meters squared per kilogram squared. All right, so that's G. Now we got the mass of the moon, which is given 7.35 by 10 to the 22 kilograms. And then we're going to divide that by, now the radius of the moon is given, but it's given in kilometers. We need it in meters because of the units of G here. So we're going to make a conversion. 1.74 times 10 to the 3, and then kilo is another 10 to the 3. So kilo means 1,000. And now we're in meters and we're going to square that. And so really you could just say, well, that's like 10 to the 6, right? So 1.74 by 10 to the 6 meters quantity squared. Now on Friday, I left it to the students in class to crunch those numbers themselves. And some of you did, and you were correct, and some of you did, and you were incorrect. If you didn't get this right, go ahead and try it now. Try it in your own calculator. If you're watching this on YouTube, go ahead and pause the video, get your calculator out, and try it yourself. All right, welcome back. Did you get 1.6? If so, then you did it correct. Leave it down in the comments below. The question goes on to read, a satellite is in a circular orbit about the moon at a height of 320 kilometers above its surface. Calculate the time for the satellite to complete one orbit of the moon. All right, you should be able to take care of that, no problem. We're going to use some of the same physics that we've been discussing, and it looks very similar to the calculation that we just did, except for instead of setting, well, we're still going to take Newton's second law, right? But now we're going to consider the acceleration that is acting towards the center of the circle, right? So this is F equals ma, but it's going to be the centripetal force is equal to mass times centripetal acceleration. Centripetal acceleration is v squared over r. So we get this expression for centripetal force. We know that it's provided by gravity. So the same equation for gravity that we just used, we're going to set equal to centripetal force, knowing that that's the thing that's keeping, you know, the satellite in orbit about the moon. It doesn't matter how massive that satellite is. One of the radii cancels 2, and we get the familiar orbital velocity equation. So orbital velocity squared is gm over r, and so we could take the square root of both sides and have, you know, the velocity by itself would be equal to the square root of this. What we want to also consider is that for an object moving in a circle, velocity in general being distance over time, the distance around a circle is going to be 2 pi r. So we make a substitution here for velocity, 2 pi r over t. All right, so velocity is 2 pi r over t. So we'll take 2 pi r over t. That quantity is squared, right? There's our v squared. It's equal to gm over r. Square everything. You get this. And then if we times both sides by t squared and multiply both sides by r over gm, it's a lot to keep track of there, but we got time squared all by itself, and we're trying to solve for time, right? So these gm's cancel, these r's cancel, and we get, I'll write it up here, t squared, right? That's that t squared, is equal to everything over here. So we got 4 pi squared, and then this r combines with these r squareds to give us 4 pi squared r cubed over gm. All right, and if we were to take the square root of both sides of that, then we'd have our subject time isolated. Substituting in values, we've got 4 times pi squared times the radius. Now the radius does require a calculation. We need to consider that the satellite is separated from the moon by its entire radius plus the 320 kilometers above the surface. And so the satellite up here is the total distance from the center of the moon, the radius, which was given previously as 1.74 by 10 to the 6 meters, plus another 320 by 10 to the 3 meters, right? So now we're in meters, right? Convert this kilometers also into meters, change that kilo 10 to the 3. And so the radius that we substitute here is going to be the sum of the 320 kilometers above the surface and the radius of the moon itself. Again, we consider that all the mass of the moon exists at its center, so that an object on its surface would feel 1.6 newtons per kilogram. That is the force acting on each unit mass on its surface, that we calculated a moment ago. .74 by 10 to the 6 plus 320 times 10 to the 3 is 2.06 by 10 to the 6. And so R is 2.06 by 10 to the 6 meters. Don't forget to cube that in your numerator, divided by 6.67 by 10 to the minus 11. And then the mass of the moon is still 7.35 by 10 to the 22 kilograms. If you type all that in correctly, then you're going to have time squared, right? So the very last thing to do would be to take all of it and raise it to the 1/2 power. That's the same thing as taking a square root. All right, for the benefit of everybody following along on YouTube, I'm going to put a calculator on the screen there. I'm going to clear some of this working off. All right, and let's crunch these numbers here together. So we got 4 times pi squared equals. Now we're going to multiply that by 2.06 by 10 to the 6. And we've got to cube that quantity. I think I put times 106. Do over. 4 times pi squared times 2.06 times 10 to the 6 cubed. All right. Divided by G, which is 6.67. Note the use of grouping symbols when you're dividing by something in scientific notation. That's something we talked about before. Finally, divide by the mass. All right, so that's everything underneath the radical. Remember that you're solving for time squared the way we had it there, so you still need to take the square root. And I get a final answer. You can see it right there. 8,390 seconds. A little over 2 hours it would take that satellite to orbit. This has been another worked example with Dr. Schleif. We'll see you next time.